So hi everyone and welcome to today's class. Today we're looking at correlation and regression, and the objective of today's class is to use R to show how to perform basic regression analysis, including plots for model checking and the display of confidence and prediction intervals. Later on, we shall also be using R to describe correlation in both its parametric and non-parametric variants. So I want us to recap the concept of simple linear regression and some of the basic assumptions revolving around the parameter estimation. So on a simple linear regression, of course, we'll be considering a regression model where we have only two variables, one dependent and one independent. So the model, the simple linear regression model, is given by yi, which is equal to beta naught plus beta 1 of x plus the errors, or plus the error term, where I starts from 1 all the way to n, where n is the number of observations. I'm going to label this as equation number 1. So here, the assumption is that, so we say that in which the errors for the error term are assumed, the errors assumed to be independent and also normally distributed with mean 0 and variance sigma squared. So that's our key assumption in this kind of model. Okay. Then we say that the non-stochastic part, the non-random part, in other words, the non-random part of equation 1 describes yi as lying on a straight line. Whose slope is beta 1. Okay, so this is what you're calling the non-random part. That's the non-random part. And then this is the random part of the model. This is the non-random. And then this is the random part of the model. So we're saying that the non-random part describes y as lying on a straight line, whose slope is given by that, and cutting the y-axis at the point beta naught, and cutting the vertical axis, or let's say the y-axis, at the point beta naught. So beta naught is the y-intercept. Okay. Then we say that the parameters beta naught, beta 1, and sigma squared may be estimated using, we mentioned that there are other methods, but we are only referring to this particular method, may be estimated using the OLS method. The OLS method, by finding the values of, beta naught and beta 1 that minimize the residual sum of squares. Okay, and the residual sum of squares are given by this formula. So SS resid, that is sum of squares residues, is given by this summation. Then you have yi minus beta naught estimate plus beta 1 estimate x, like that, then square. Okay, then we need to recall or to note, so I'll call this one my equation number 2. And we need to note that yi estimate is what is defined by beta naught hat plus beta 1 hat of x, meaning that the whole of this item here is y hat like that. We are summing these things over the i's, or from I is equal to 1 all the way to n. So let me put those details there. So for I starting from 1 all the way to n, so like that. Okay. So in some other places we'll find this sum of squares recede will be given by summation of yi minus y hat, okay, squared. So it's the same thing. So for I starting from 1 all the way to n, so it's the same thing. But let's keep the longer format as given in question number 2 here. Okay. Then, so we said that for you to minimize equation number 2, you apply differentiation, and more particularly, you apply what we call partial derivatives. So you differentiate equation number 2 with respect to beta naught, and then you equate that to 0, because when you're trying to minimize or to optimize, you equate the first derivative to 0. We find, let's say, if I call SS recede, if I replace that with the letter S for simplicity, I'll be talking about S is equal to summation of yi minus beta naught plus beta 1. So that's what I have. So I'll be trying to find the partial derivative of S with respect to beta naught. Then you equate that to 0. Then you also do partial derivative of S with respect to beta 1, and you equate that to 0. And when you simplify these equations here, you will end up with what we call the normal equations. You'll end up with what we call the normal equations. And normal equations are just a system of two linear equations which can be solved simultaneously, to find the values of beta naught and beta 1. But we'll not be going to those details. We just say that when you minimize that function, and then you will get the formula of beta 1 and beta naught as follows. So we say that minimizing equation number 2 through partial derivatives or through partial differentiation. Through partial differentiation with respect to beta naught and beta 1 estimate, we obtain the following. We obtain these. Okay. So so we get beta 1 estimate be given by summation of xi minus x bar, yi minus y bar, divide everything by summation of xi minus x bar squared. And we are summing these guys from 1 all the way to n, even this one, I is equal to 1 all the way to n. All right, so we can call this one our equation number 3. And then we also get beta naught estimate as y bar minus beta 1 estimate multiplied by x bar. You can call this one equation number 4. So equation number 3 is a definition of formula. There's no problem if you work with it directly, but it is much more easier and convenient to work with a computational formula, a computational format of equation number 3. And the computational format is given by this note. We need to note that summation of xi minus, sorry, I need to keep it simple. So x minus x bar, if you take that squared, it is the same as summation of x squared minus n x bar squared. So please notice that it is x bar which is squared in this case. And then using the same logic, it can be shown that if you have x minus x bar, this is the numerator of equation number 3. And you have y minus y bar. This is the same as summation of x y minus n x bar y bar. So you will find that it is easier to work with equation number 3 when it is of the format given in the note. So that means if you want to write equation 3 in a different format, you will have beta 1 is equal to summation of xy minus n x bar y bar, okay, divided by summation of x squared minus n x bar squared. So the calculations here are less bulky compared to the definition of formula. All right, so that's how you get the estimates of the slope and the vertical intercept, or the y-intercept, sorry. Okay. Then the next concept that I want us to recall is what we call the residual variance. Remember, we said that there are 3 parameters that we need to figure out, beta naught, beta 1, and sigma squared. So here we talk about the residual variance. The residual variance. The residual variance, that is the variance of the error term. The residual variance is estimated by sigma. We have a hat, so sigma squared, but you need to put a subscript u for, not u, for e. Sometimes I interchange u and e, or maybe sometimes I'll be forgetting. So this is of e, which is equal to s sum of squares due to the residual divided by n minus 2. So that's how you estimate the residual variance. Remember, the residual variance should be like this, huh? Okay, but it is always unknown. Always unknown. So you estimate it using the sample counterpart, which is sigma hat, like that, of the error, which is given by the formula given above there. Of course, the numerator is what we defined earlier here. The numerator is what we defined earlier here. Maybe an easier way of writing that denominator, the numerator will be, if you take y I minus y hat squared, then you sum. That's how the numerator looks like. And the divisor will look like this. That's the formula of the estimate of the residual variance. Okay, then we say that, and the standard deviation. So we call this one equation number, so let's call this one equation number 5. We say that the standard deviation of equation number 5 and the standard deviation of equation number 5, okay, is called the standard error of the regression. It's called the standard error of the regression. I guess by now you understand that the word standard error is just another way of saying standard deviation. It's only that we strictly use standard error in the context of getting summary values for statistics. Like you see, this is a statistic because it's being obtained from the sample. Okay, just like X bar is obtained from the sample. So if you get several values of X bar, okay, from samples which are coming from the same population, then you try to find the standard deviation of that. Standard deviation of X bar, which I'm calling, where X bar here is contains X bar 1, X bar 2, and so on and so forth, all the way to maybe X bar K. Then this standard deviation is called the standard error of the mean, like that. So the same case here, we're talking about the standard deviation of equation number 5. So technically, that is a standard error of, it's called the standard error. And in this case, it's the standard error of the regression. Sorry, there's a typing error here. Standard error of the regression. Okay, so that's called the standard error of the regression. And usually, as you would expect, if you take the square root of equation number 5, you'll observe this. So you can say comma sigma hat of the error, like that. So that's the standard error of the regression. These are very important summary value in regression analysis, especially when you go to hypothesis testing. If you want to check the significance of the model, then we'll be using the standard error at some point. Okay. Yeah, then we continue by saying that the objective in regression analysis, the objective in regression analysis is to test this hypothesis, is to test the hypothesis that H naught, that beta 1 is equal to 0. So these are objective. We want to check whether the slope coefficient is different from 0. Okay. In many words, we're saying that that is if the line is horizontal, if the line is horizontal, and thus y has a distribution, that is the same, or that does not change whatever the values of x, So we're trying to test the hypothesis that x has no effect on y. Basically, that's what we are doing. When you say that H naught beta 1 is equal to 0, that means that line is horizontal, okay? Meaning that x has no effect. X has no effect on the estimated value of y, okay? And of course, now there's the alternative hypothesis, which can take different formats. But as we mentioned in our previous class, is that the alternative hypothesis by default is a two-tailed test, okay? But before we go there, let's say that when H naught is true, that the t-test statistic is obtained by the t-test statistic is obtained by dividing beta 1 estimate by its standard error. Okay, that is, you divide that by the standard error of beta 1, in this case. Okay. All right. So i.e., we're saying that the test statistic is given by t, which is beta 1 hat. Of course, there should be a -0 because there should be the beta naught. The hypothetical value in this case is 0. Ideally, this should be like that, divided by the standard error of the estimate, like that. But of course, there's no need for us to put this. Okay. And this t statistic here has a t distribution with n minus 2 degrees of freedom, or with the degrees of freedom equal to n minus 2. Then we may need to note that it's meaningless. It is meaningless to test the hypothesis at H naught that beta naught is equal to 0. So it is not important to test this hypothesis, okay? Because we're just saying that we are testing the hypothesis that the line, this is your x, this is your y. We are testing the hypothesis that the line passes here. You see, there's no good reason to imagine the line should pass there. So basically, this hypothesis is not important, so you don't need to test it. So we can say that since there is no natural reason, to believe that the line should go through the origin. There's no reason why we should imagine that the line is passing through the origin. So usually we rarely test that the significance of beta naught. Now that's the theory, a little bit of the theory that we'll be applying now, or that will be driving our actions in R. Okay, so let's now go to R. So let's have a subheading using R, perform simple linear regression. Okay, and here the main function that we use here is the LM function. So the function LM, so that kind of function is used, and this function is also used in multiple linear regression. As long as it's a linear model, we use LM. So LM is just linear model. So that's where the L comes from, and the M. And we say that the argument to LM, or to this particular function, is a model formula. So we use a model formula inside this function, in which the tilde symbol is this symbol here, should be read as this, described by. So we talk about y being described by x, something like that. So like this, y described by x. So the function will look like this. So this is how you write your code in R. So you will write, this is LM, then you have your y described by x. So this is what you're calling the model formula. This is what you're calling the model formula. This is a tilde. So this just means you fit a linear model where y is described by x. So in other words, you are fitting this model, y is equal to beta naught plus beta 1 of x. Okay, if you are fitting, let's say, a multiple linear regression model with two explanatory variables, for example, if you want to fit this beta naught plus beta 1 x1 plus beta 2 x2, if you want to fit that, these are estimates, of course, then your R code will be LM, then you have y, then you have now x1 plus x2, then you close. That's how you will fit it in R. Okay, so in addition to this, when you run this, we'll get the coefficients. You will get the regression coefficient, that is beta naught, and the slope coefficient or coefficients. But there is much more information that you may also want to get. So it's also good for you to, instead of running the code like this, you prefer to assign it a name. You can assign this function a name. You can call it maybe my fit is you assign this formula here. Then now you can be calling that name to extract different types of output. I'll be showing that much more practically. Then we say that a basic extractor, if you want to extract different parts of the output, extractor function is summary. So once you assign this item here a name, then you can call summary of, so this is how you'll be typing it in R, summary. Then you write now the name, the object that you want to summarize. Okay, I want us to go to R and have some data sets from there. So I want us to consider, consider this data in R. Consider this data called it's called in this library, Introduction to Statistics with R, this kind of library. So let's go to R. So we need to call the library first. This is a library that we have already installed. So you call the library. Then this is the data that I want us to consider for illustration purposes. So I want to attach the data. Attach the data. Okay. Then I want to have a look at how the data looks like. So, but I have the look. I'll type the code in the console because I don't want to keep that in my R script. So I want to have a look at how this data looks like. And this is the data. So we have two variables, blood.glucose and shot.velocity. So we can just scroll through and you will notice that observation number 16 has some missing value and a shot.velocity, okay? And so on and so forth. So there are 24 observations. There are 24 observations, okay? So if you want to understand the meaning of this data, what the data is all about, you can also query in R. So you come here and ask, what is this data all about? You can ask that query. Then when you come here, once you click here, you see this is ventricular shortening velocity. Okay, so that is what the data is all about. So this data has 24 rows and 2 columns. It contains ventricular shortening velocity and blood glucose for type 1 diabetic patients. Okay, and then yeah, that is basically the description of that data. All right. So you may want to look at a few of the observations. If you don't want to view everything, you may say head. Then you want to see, once you type head, then the name of the data set, it gives you the first 6 observations. Okay, so this is how it looks like. So you see the head, the top 6 observations. Okay, you may also want to look at the last 6. The last 6. So like this, if you use tail, so you see you get the last 6. So you see this is 24, 23, 21, and so on and so forth. So you see the bottom 6 observations. If you don't want to see all the 6, you can say, let's say I can say head. You can modify this to see any number that you want. For example, I can say head, and I want to see only 3, the first 3, okay? So you'll get these. The same case can happen with the tail. So you can say you want to see the last 5 or the last 10. You can also choose to see a random sample from here, okay? So you can say, you can insert here sample. So you pick, you sample from 1 to 24, you sample like 5 of them, or you sample like 3 of them randomly. So let's try the code. Yeah, so you can try the code and see how you can select a random sample from the list of observations that we have. I think we were getting some errors. All right, so from there, let's say, suppose we want to fit a linear regression model. So let's fit a simple linear regression model. To predicting short dot velocity using blood glucose, using blood dot glucose. That's what we want to do. And we're saying that the basic function is LM. So we use LM. Already I've attached the data, so I can just call the variables directly. So we say LM, then we say short dot velocity. Then this is the tiled symbol. Then blood glucose. That. Okay. So when you run this code, it will give you the output, but it will give you limited output. It will only give you the coefficients. You can see once you do that, you'll get the coefficients. Okay, here. So it is much more, it is better if you assign a name to this. So you can say, I can call this one my fit. I can assign it a name like that. I can assign it a name like that. Okay. So now I'll be calling, let me call this my fit one because I'll be fitting some others. Okay. Then if you want to get the output, you say summary. Summary my fit one. Summary my fit one. So this will give you complete output. Okay. So, and as you can see, this is just a duplication of the formula that we used. Then we have the residuals. You're given a summary of the residuals. You know the residuals, we assume that the residuals have a mean of 0. That's one of the assumptions, that the error term has a mean of 0 and constant variance. So the minimum value in the residuals is minus 0.40 something. The first quartile is that much. The median, and we can, if we assume that the residuals are normally distributed, then the median and the mean should be very close, actually should be equal theoretically. So we know that the mean is around here. Then the third quartile or the upper quartile is here, and the maximum value of the residuals. So again, if the residuals are normally distributed, we expect the absolute value of the largest number and the absolute value of the smallest number to be almost equal. So these are symmetrical distribution, and we expect that the mean should be around here. Okay. Then we have the other part of output. These are the coefficients. Okay. And we have the intercept, that is your beta naught estimate, which is 1.09 etc. Then we have the estimate of beta 1. Beta 1 is the coefficient of blood glucose, or our X variable, which is this much. Then we have the standard errors corresponding to each estimate. So this is the standard error corresponding to beta naught, or the estimate of beta naught. And this is standard error corresponding to the estimate of, or this value here, the estimate of beta 1. Then the t value, we said that the t value is given by the estimate. If you take this estimate here, divide by the corresponding standard error, that will give you this t value. Then this one again is given by, you take this value, divide by this. Of course, the hypothesis that we are testing by default is that the slope coefficient is equal to 0. That's why we're only taking this divided by that. Then using these t values, you can check whether they are significant using either critical values read from t tables or using p values. Luckily, your R gives you the p values, okay? And we said that we'll not focus on this, the significance of the intercept. So the p value corresponding to the slope coefficient is this much, 0.0479, okay? And by default, we use alpha, or the level of significance is 5%. So this shows that this coefficient here is significant at alpha is 5%, okay? There's some additional information here, the stars, okay? So the stars tell you the level at which this estimate is significant, and the explanation is down here. So when you have 3 stars, like the first scenario, it means that your estimate is significant for alpha, that is for level of significance greater than 0, but less than 0.001. So this value here is significant at any alpha which is less than 0.001. Okay. So when you have 2 stars, it means that your statistic is significant at an alpha level which is greater than 0.01, but less than 0.01. So clearly, if your alpha is 2 star, it means that it's significant at any alpha which is less than this much. Okay. Then of course 1 star means that it is significant for alpha less than 0.05, and then but greater than 0.01, and so on and so forth. Okay. So you can also have a dot. A dot means that it is significant within that interval. And if there's nothing, if it is blank, it means that it is significant within. In most of the cases, this will not be significant. So significance is only from alpha. Most of the cases we use alpha is 5%, 1%, and sometimes 10%. Sometimes we use 10%. So when it is 1 dot, it means that it's significant at 10%. Then below here we have the residual standard error. Okay. So that's something that we have already explained in the slides, that the residual standard error, that is the sigma estimate of the error term, which is given by here. So if you square this value here, you'll get the estimate of the residual variance. Okay. Then on 21 degrees of freedom, that is and then you are being told that one observation has been deleted due to missingness. As we saw when you were looking at the data, we saw that observation number 16 had a missing value. So regression analysis, by default, the missing value is deleted. So it's not part of the analysis. Then we have multiple R square. Okay. So this tells you that we have around 17.37% of the variation in blood in short velocity explained by blood glucose. Okay, so that is R squared. In the case of simple linear regression, this multiple R squared is equal to the Pearson's correlation coefficient squared, or small r squared. Okay, so meaning that if you take the square root of this guy, you will get R. Okay, and of course, if you don't want to use multiple R squared, you can also use adjusted R squared. And then we have the F statistic. Okay, and the F is actually checking if the variance explained by the model and the variance which is not explained by the model are actually equal. So it's some variance is the mean sum of squares explained divided by the mean sum of squares unexplained. And the degrees of freedom will be 1 on the numerator and 21 on the divisor. And the p-value corresponding to this F statistic is this much here. The p-value is given by this. Okay, you will notice that when you're doing a simple linear regression, actually this F statistic may not be adding a lot of value. Okay, because basically this value is just this number here, is the t value squared. If you take 2.101 squared, if you square this value, you will get this value here, or very close to this value. So in simple linear regression, actually the F statistic may not be very informative. So because we're just squaring the t, if you take t squared, you'll get this F, and you'll notice that the p value is the same. P value is the same. So actually for simple linear, you can just interpret your results up to here. Maybe you may want to talk about the multiple R squared, but not the F statistic. If at all you have talked about the significance of the slope coefficient, you may not want to talk about the F statistic because it will not give you any additional information. So basically, that is how you perform simple linear regression in R. Okay, I don't know if there is any question. Yeah, so after that, after learning how to fit a linear regression and a simple linear regression model and extracting the output using R, I want us to go to something else, that is the regression, how to obtain the regression residues and also the fitted values. And the key functions that we shall be using here are fitted, the function fitted, and another function resid to extract the required output. So we're going back to R and see how to implement these functions. So before we extract the residuals, let's have a look at a scatter plot for the observations that we are dealing with. So we have blood, glucose, and then we have another variable is called short velocity. Okay. Then we may want to, if you want to include a title to your plot, and I want the title to be on top, you can vary the location as you wish. So you can have scatter plot. Scatter plot with fitted line. We have our scatter plot with the fitted line. That's a straight line. That's the regression line fitted within the scatter plot. Okay. So this will give you the scatter plot. These are the raw observations. Okay, short velocity on the vertical axis, then blood glucose. Then if you want to insert a straight line, the line of best fit passing through the points, you use upline. Then you say, remember the equation is given by my fit one. My fit one. Okay. So that is the line of fit. The straight line. This is the equation that we're talking about. Okay, it is cutting the vertical axis somewhere here, and then that's the slope of the line. Okay. So if you want to observe the fitted values, these are the y-hats. So you will use this function fitted, and then fitted of my fit one. These are the fitted values. These are the y-hats. Okay. So, and these numbers on top here are the rows. These are the observations, the first observation and the corresponding fitted value, the second observation and the fitted value, all the way up to the 24th observation. Remember, there are 24 observations and the fitted value. So you will notice that the first row contains the first 7 observations. The second row has 8, 9, 10, 11, 12, 13, 14, which is okay. Then we have the third row contains 15, but there's no 16. Hope you can see that, that the 16th observation has been skipped, because by default, the LM function will delete or will skip all the missing observations. So remember, when you viewed the data, we saw that observation number 16 had some NA. That is the value were missing. And the rest are okay. So 17, 18, 19, 20, all the way to 24. So these are the fitted values. Okay. That means if you take an equation which has this value as the slope coefficient and as the y-intercept, and these are the slope coefficient, then you use the values of data, the values of x, that is blood or glucose values given in the data. You substitute them in that equation, you will get these values of y. Maybe we can do that. So we're saying that the fitted values given here, the 16th observation is skipped, and the output we have here is can be quickly obtained using the coefficients that we got here. So let me see if you get the summary. Yeah. So if I form an equation here using the fitted lines, using the estimated values of beta naught and beta 1. So this is the kind of equation I'm calling it y fitted is 1 point all this plus that times blood glucose, where blood glucose is the observed data. So if you run this code, you will get values which are very close to what we got using the fitted function. They're very close. Of course, they are slightly different because of the missing observation, which was deleted at some point. So which is not affected here, but the values are very close. These values, so the first one is 1.433, this one is 1.433 something, 1.334 something, this is 1.335, and so on and so forth. Okay, then the residuals is actually the difference between the observed values and the fitted value. So if you take your short dot velocity, then you minus your fitted values. I'm using the ones that I computed manually before I use the R function. So this is what I'll get. These are the residuals for the first individual, for the second individual, and so on and so forth. So this is what I'm saying, that should be having a mean 0, and they should be independent. They should be independent and have a constant variance. So you can see this one is missing here. Okay, but a quick way of doing all that is to use the resid function as mentioned earlier. So you say resid for residuals, then the resid for my fit 1. Okay, so these are the values. As you can see, they are not very different from what we got by hand. So this is 0.326, almost the same, all that. Some slight variations because of the reasons I gave earlier on. So you notice that this is the first individual, the 5th, all the way. The 16th one is skipped again. As you can see, we are moving from 15 to 17. So the 16th one is skipped because it has missing observations. So that's how you extract your residues. So when we talk about residual variance, we talk about the the variance of these guys. Okay, if you just click, if you just take these, you say copy, then you say variance. I can use variance, I can use standard deviation. Actually, I can use standard deviation. So if I use standard deviation of this, okay, so you'll get 0.21 something. Yeah? I don't know how that is different from what we got earlier on. Okay, it might be slightly different, but we need to take, we need to square them, and then we divide by n minus 2. Then after that, we take the square root. So if we do this, if we take these values, we square them, because we expect the mean theoretically to be 0, the mean of the residues to be 0. So if I square this, then I sum them, and do that. Then after that, we divide by n minus 2. And this calculation was based on 23 observations, not 24. So I take 23 minus 2, so I divide by 21. Okay. Then after that, I take the square root of that. You will get this. This is the standard error of the regression. So maybe you can check with our output. Let's recall summary of my fit 1. If you do summary of my fit 1, you see it might be different, but is very close. The residual standard error 0.2167, and not very different, by the way. If you look at this, 0.2167. Yeah, they are very close. So basically, what you're calling here the residual standard error is just the standard deviation of the residues. But it's good to notice that the degrees of freedom is n minus 1. It's n minus 1. So if you use the direct formula of calculating standard deviation, that is, if you just do SD of these residues, you are likely to get some maybe slightly different number, because the division here, if we use this formula, the division will be by n minus 1. You'll be dividing by n minus 1, whereas you should be dividing by n minus 2. Okay, so that's basically it. If you want to extract the fitted values and the residues for some given data. I don't know whether there is any question regarding that. So whenever you have some values in the data being missing, that is when you have some missing observations, by default, R deletes the observations or the individuals who have missing values. So, and the risk is that if you have many individuals having missing values, they are going to be deleted, and that might affect your size of sample. So sometimes you may want to go around that through using appropriate methods to impute the missing values. But for now, we shall just show how to a nice way of skipping the missing value in your analysis. And you're going to use the na.action function in R. So we can start by saying that option So you can start by saying options. Then here you say, what do you want to do with the missing values? NA action is you exclude them. You exclude them in the analysis. Okay. NA action. So NA is the symbol that we use for missing values. NA. So you can instruct R to do that, to exclude all missing observations in your analysis. Okay. Then now let's refit the regression model by skipping the missing values. So I can call my new fit as my fit 2, and then I assign the name LM. Then we have short dot velocity. Then here we have, so we explain this by blood glucose. Yeah, so I can rerun the model by excluding the missing values like that. Okay. Then you may want to do the summary. If you do the summary of my fit 2, get the coefficients might not have changed very much. Okay. Then from there, let's do this. Let's plot. I want us to plot the residuals and the fitted values on the same axis. I want us to plot the residuals and the fitted values on the same axis. So let's have this plot here. I want to plot blood glucose. And then you also have velocity. Then I want the title of my plot to be on top there. And I want this to be scatter plot. With the fitted line, residual line segments. As you know, the residuals are the vertical distances between the fitted line and the observed values. Okay, so let me put it here so that it can be seen clearly. Okay, so let's see how this one looks like. So that's a scatter plot, similar to what we had earlier on. And then I want to insert the straight line. So in this case, I'll use the function lines, not the up line. So then I have blood glucose. Then we have, I want the fitted values of my fit 2. So fitted of my fit 2, my second fit. Okay, so this would be the regression line using the equation that we have come up with. So that will give me that straight line. Okay, then now I can add the segments showing the errors. The errors are vertical distances from the fitted line, from the observations to the fitted line. So those are what we're calling the errors, or the residuals. So those are the segments that I want to add on the same plot. So I'll use the function segments, then I say blood glucose, and then fitted my fit 2 Then here we have blood glucose. Then we have short velocity. Then let's see how this one unfolds. So you have those vertical lines. Those are the residuals. It's actually the errors, the size of the errors. Okay, those are the errors. So the vertical distances from the observation to the treated line. So when we talk about the OLS method, we want to minimize a sum of the square of these distances. So if you take these values, you square them. That means even the negative ones will become positive when you square them. Then you sum them. You want a line that will minimize that. That's the line of best fit. Okay, so that's how you can show a scatter plot with a fitted line and residual line segments using that. Then sometimes when you are doing the modeling, you may want to have a look at the behavior of the residues, especially in relation to the predicted values. So you can have a simple plot of residues versus the fitted values. Because one of the assumptions of the OLS is that the residuals have a mean of 0 and constant variance. So we want to have a look at it. If it happens that, and also the concept of independence, that the residuals are independent. So if you notice that the residuals don't look like they're independent, if they seem to be following some trend, that means you may need to go back to a model and check what you need to adjust. Maybe there's a term which has been skipped, or maybe there's some transformation of the data that is required for you to assume residuals which are well behaved. So if you want to have a look at the residuals, you can do plot. Then you say fitted values of my fit. That will go to your x-axis. So you need the fitted values. Those are your y-hats, and then the residue of the same fit go on the vertical axis. My fit 2. Okay. So this is how your residuals will look like when you check them against the fitted value is just a y. Okay. So if you look at the behavior of the residuals, you are looking for if the mean, does the mean look like it's 0? If you look at the mean, does it look like it's 0? Okay. Because we expect the mean to be around the center like that. Okay. Or do we see that the residuals seem to be forming a trend, maybe a positive trend like that? They seem to be increasing as you increase the values of the estimated values of y. So if that is the case, you know that there's a problem with the model, or maybe are they sloping and so on and so forth. Okay, but from the look of things, though sometimes there might be some subjectivity in the way you interpret some visual diagrams, when you look at these residuals, they don't seem to be having a mean which is different from 0. They also don't. They also look to be independent. If you look at them, that is, if you look at if you are to estimate the correlation, you expect it to be very close to 0, if not 0. Okay, maybe that if you try to do this, though we don't recommend you to do this. If you do this, recede of my fit 2, if you look at that, and then you also have fitted. You have fitted then my fit 2 like that. There's a problem somewhere, but we don't expect that the correlation will be very different from 0 by looking at this, because there is no trend. There is no evidence of any trend when you look at these observations. So independence looks like it's ascertained, and then the assumption that the mean of the residuals is 0 looks like it is true if you look at it like this, and so on and so forth. And if you look at the spread, the variation looks like it's constant. So we can also reasonably assume that the variance of the errors or the residues is constant in this case. Okay, so any question there? So maybe a better way to analyze the residues is to use a QQ plot. So So that's what I want us to look at next. And I want us to look at a scenario, to look at a simulated case of a normally distributed residues. We simulate some normally distributed residues, then we compare them with what we have here. If we do a QQ plot, how different are they, or how similar are they? So let's do that. So in short, we're saying that you want to perform basic residual analysis when you are performing a linear regression model. And as mentioned earlier, we are going to simulate an ideal situation where the residues are actually coming from a normal distribution with mean 0 and some constant variance. Then we check the residual plot against what we have from our example. So we want to perform simple residual analysis using R, and I want us to have a look at the ideal situation. Of course, the ideal situation cannot be replicated when you have some actual data set. So to do that, I'm going to simulate a random variable X, which has a mean 0. But because I want to be able to replicate my results anytime I run my code, I set seed. So I say set seed, and then I give it this identity here. Okay. So you can use any other values. You don't have to use the ones that I've given here. Just use your numbers, your own numbers. You will not get the same values, but you will be getting those particular values anytime you run that particular code. So when I run this, then I run X. So I can put brackets at the beginning and also brackets at the end, so that I just get the output anytime I run that line. So if you look at these observations, these are 10,000, and some of them will not be displayed. So the first value is these, and the second value is these. So maybe you may want to note those two. If I had not set seed, then I repeat this line. I run this line 32. If I had not set seed, I'll be getting different values of X every time I run line 32. But because I've done this, even when I run this again, even tomorrow and next year, when I do that, I'll be getting the same sample. I'll be getting the same sample. If you go up, you'll notice that these were the first observations and the second ones in the earlier case. Okay, then I want us to have a look at how the QQ plot will look like for this scenario. This is a random variable with mean 0 and constant variance. Okay, variance which is equal to 1. Okay, so let's run a QQ norm of X. And how does it look like? Okay, so this is how the QQ norm will look like. The QQ plot will look like this. The QQ plot will look like this. This is a QQ plot for a normal variable. You can see the variable is normal. That's how your QQ plot will look like. Then if we say that we check the behavior of the points around the straight line. So let's add the straight line. So QQ line of X. Okay. Of course, the line is not visible because it is color black. Maybe if I use a different color, it will be more visible. There's a line, but maybe you cannot see it. So I can put color which is easy to see. I can say color is equal to use red. Use red like that. Yeah, maybe some of you can see it. I can increase the line width to make it more visible. Line width, I can say 3. Let me see what happens. Yeah, now it's more visible. When I increase the width of the line, that's what you have. So this is an ideal situation. This is how a QQ plot should look like for normally distributed random variable. Okay, we have the theoretical quantiles. Okay, these are purely normal distribution, pure normal distribution. These are the quantiles are the Z values. You remember the Z values. The middle value is the Z is equal to 0, and then we have Z is equal to 2, and around Z is equal to 3. The normal density curve dies out. From 3.5 going up, the normal density curve dies out. The same case with minus 3 point something here. Okay, that's why you are saying that the quantiles are running from 0 to around -4. because if you look at the curve, the bell-shaped curve, at around -4, the curve is very close to 0. Okay, and these are the sample quantiles. These are the quantiles that are computed from the data that we have from this sample here. If you compute quantiles from the sample that we have, then you plot them against the theoretical ones. If it's a purely normal distribution, we expect a straight line like this one. Okay, but in most of the cases, in practical scenarios, the points may not all of them lie on this straight line. Some of them will be deviating slightly. Okay, so but basically this is like our marking scheme. This is what we want to expect if the residues are normally distributed or something very close to that. All right, so let's do a QQ plot for our residues. So in our case, we'll have QQ norm. And then we have resid of my fit 2. My fit 2 like that. Okay. So you see, this is how our residues will look like. You can clearly see they are not falling on purely a straight line. This is very much expected. You can see it looks like there are some jumps here and there. Okay, so I want to see the QQ line and see whether most of the points are falling on that line. QQ line, then we have resid my fit 2. Then I want the color to be, I can also use a number to represent my color. Then I don't use quotation. I only use the quotation marks when I use the name. So I can choose another color number 7. I can't remember which color it is. Then I can say line width. I can say, let's say 4.5. You can play around with the line width the way you want. And if I run this, what do we get? Yeah, so this is how the QQ plot looks like for our case. So these are the theoretical quantiles, and this is what we have from our data. So you can see the points are not, okay, most of the points are falling on the straight line, except there are some extreme cases here. Okay, you can see that the tails, this is where the tails are found, and even here. So the tails here look like they are a bit fat, slightly, and then there seems to be some jumps here. But looking at it is not very badly off because most of the points are very close to this straight line. Okay, so maybe we can do this. If we do the histogram of resid, let's see how it looks like. My fit 2. Okay, so this is how the histogram of the residuals looks like. And this agrees with the QQ plot that not badly off. They are not badly off. So assuming that they come from a normal distribution is reasonable. Though as you can see, the tails look a little bit fat here. And then we also have these kind of jumps here. But this is expected when you have a very small sample. But if the number of observations were a little bit larger, then we don't expect this kind of jumps here. Okay, but assuming that this sample comes from a normal distribution is a reasonable kind of assumption. So basically, that's how you check the residues and the behavior of the residues. Okay, any questions there? So next, I want us to look at how to come up with the prediction and confidence bands using R. So basically, when we talk about the confidence and prediction bands, these are like a series of confidence intervals for the line and also for the observations. Okay, so if this is the line, for example, this is the predicted line, we need a series of observations which will give us the confidence interval somewhere like that. It's like the tolerance. Okay, and then when you have all the observations in the data, you may want to have some interval again containing most of the observations in the data. So something like that. So the narrower one, so we have two types of bands here, the narrow band and the wider band. So we can start by saying that fitted lines. Like when you look at this, if this is your fitted line, then clearly there's some level of uncertainty. There's some level of uncertainty, and that uncertainty is what is covered within this interval here. Okay, within this interval. Okay, so they are presented with some uncertainty bands around them. And we say that there are two kinds of bands, like the ones illustrated here, where one of them is loosely called the narrow, and the other one is called the wide band. Now, the narrow bands, also known as the confidence bands, reflect the uncertainty around the fitted line. Okay, so if there are many observations, the band will be quite narrow. So if your sample size is large, then these black lines will be very close to each other. Maybe they'll be somewhere here, very close to the fitted line if you have very many observations. Okay, meaning that the fitted line will be well determined. That's why you are always encouraged to pick a large sample when you are doing estimation. So these bands will often be curved around the center, will show some curvature, and they'll be narrowest near the center. They'll be narrowest around the center, where the center here corresponds to the mean of X and also corresponds to the mean of Y. So this is the point where the estimation has the least error. The estimation of this line, the least error is found here at the center, where the mean of X and the mean of Y intersect. Okay, then the wider bands or the prediction bands, they include the uncertainty about the future observations. So the wider bands are about the observations, not about the fitted line. So that's the basic difference. Okay, so these bands usually capture most of the observations. Some of them may be left out, but they capture most of the observations. But as you increase the size of the sample, these bands will become narrower and narrower. Though they will never collapse to a single line, they just become narrower and narrower. And what will happen is that they'll approach plus and minus 2 standard deviations. They'll approach that 2 standard deviations within the line. It'll be around 2 standard deviations within the line. So if this is your line here, if this is your line there, straight line there, we're talking about plus or minus 2 standard deviations. So here we have plus 2 standard deviations, and here we have minus 2 standard deviations. So as you pick large samples, then the curve will tend to be approaching plus and minus 2 standard deviations, but it'll never collapse into a single line, the way we expect the narrower bands to collapse when you have so many observations. So we can illustrate that in R. Using some coding here. All right, so to start us off, we are going to create a new set of values. We are going to create a new set of values for the blood glucose, because looking at the blood glucose observations, those observations are like these. Okay, as you can see, they are mixed up. They are not arranged from the smallest to the largest. I want them to be sorted. I have the option of sorting them, but there's a quick way of doing it by just getting some new set of observations of blood glucose within the interval here. So I need to know what is the minimum value of blood glucose, so that when I'm creating my new variable, it includes the smallest value of the observed data. So blood glucose, the minimum value is 4.2, and then the maximum value of blood glucose is 19.5. So I want a new set of observations, which I'm calling my new data, which I want it in form of a data frame. And the variable name will be blood glucose, starting from 4, the smallest value, and the largest value is 20. That will accommodate these two. Okay. So this is what we'll have. So these are my observations. Okay. So I have a data frame here, a new data frame with only one variable called blood glucose. and they are now arranged from the smallest to the largest. They are not mixed up. If they are mixed up, you will end up with a line which looks like that. Huh? And it may not be possible for you to come up with a nice confidence interval for these. Huh? So this is what I have, and these are the values that I'm going to substitute into my simple linear equation using the estimated values of beta naught and beta 1. So this is what will give me the estimated the confidence bands and also the fitted lines. All right, so then after that, I want to get the predicted values using my new set of values. So I can call this predicted. This is now this will give me the limits of the predicted confidence band, okay, of the predicted confidence interval. So this is so I say predict. I predict. Then there are some optional arguments that now I must say. So my fit, I'm still using my fit 2. Then you say interval. What kind of interval are you looking for? Is it the predicted interval or the confidence interval? So here you can say the predicted interval. You can say P, or you can just say the word predicted. You can write in full by saying either predicted. So let me write predicted. You can say that. Huh? Not predicted, prediction, sorry, prediction. Huh? Should be prediction, not predicted. Or you can just use P to avoid some of those errors. Huh? Then which data do I want to use to do that? Which values of X? X here is my blood glucose. Huh? So my X here, which we call new data, this is an optional argument. So the data that I want to use is what I called my new data. So I'm substituting those new values of X. This is what we'll end up with. Huh? So let me see why this is not working. There's an error here. There's an error here. This is supposed to be like that. Okay, so this is what you have. So if you want to have a look at these values, you can put bracket there and another bracket there. So these are the observations. You see, so these are the fitted values. These are the fitted values. Then this is the lower confidence band, and this is the upper confidence band, or the predicted confidence interval. Okay, so these are the upper values and the lower values. So this is what I want to plot. I want to plot a straight line which represents this point, and another curve which represents the lower and the upper. Okay, so that will give me the prediction band. And then I also want a similar one for the confidence band. So using a similar code, so I use a similar code. I only change this bit here. Remember, all these things are optional. All these things are optional. If you don't say which data, it will use the default data which you used up there. Okay. All right. So I want to copy this. I want to copy this code. I paste it down here. But now I wanted to call it predicted confidence band. So here I'll say predict the same my fit to interval. So this one will be confidence. You can use the word confidence, or you can just say C. You can just use the letter C only. Confidence. Then I'm using the same new values of my X variable, like that. Okay. So the output will be similar to what we saw earlier, to what we saw in the previous code. So the confidence band will be given by this. So these are the fitted values. We expect these values here to be the same with the ones that I got here. These ones, they are the same. But these confidence limits are different. The lower and the upper confidence values are different in the two scenarios. Huh? So as you can see, these two are not the same as this. Okay, so you can see one of them is wider than the other one, and that is what is expected. So I want us to plot this information on the same axis, then we see what we are going to end up with. So let's do the plot. So let's do the necessary plot. So we're going to have plot. We're going to start with a scatter plot here of blood glucose, and then short velocity. Okay. Then I want to adjust the limits on the vertical axis. I want to adjust the limits of my vertical axis. And also, yeah, the vertical axis especially, because we're only changing the items on the x-axis have no problem. So the problem might be on the values on the vertical axis. So I want to make sure that I don't miss out any values. So I can say y-lim, I want to adjust my limits on the vertical axis. So y-lim, then I say the range should be from where? I want this to start from, to include the lowest value should be coming from short dot velocity, and then the largest value to come from predicted P. Okay, and then I also want to remove any missing values in that data, because if I don't remove and there are some missing values, I might get some errors. So na.remove is true. So I want that statement to be true. Okay. Then what else can we say here? Let me put this. Let me bring this line down here. Make my work easier. Okay. Then so that is true. Then something else that I want to add, which bracket is this? So after that, I also want to label my axis. Maybe this is something that we have not been doing. I want to label my axis. So on top, I want this diagram to have this title. On top, I want this to be plot with confidence. Plot with the confidence and tolerance limits. Let's say tolerance bands. Plot with those two, and then that's on the top of the diagram. Then I also want to have I want to label the axis nicely. I'm going to have X lab. I want to label my x-axis. I want to put a meaningful name here. So the name here is fasting blood glucose. Fasting blood glucose. I think we saw this when we were checking the description of the data. Blood.glucose was meaning or means blood fasting blood glucose. Then I also want to have something else here to label the y-axis, y lab. I want time to be there. The label on the vertical axis is ventricular shortening velocity. Ventricular shortening. Okay. Shortening velocity. There are some typos. Velocity, like that. So that should be the label on the vertical axis. Yeah, basically that. I guess that that should be it. Those are the main things that I want to see. Okay, there are no challenges here. So I think we were just checking whether there is any error in the code. And then when you run this code, I need enough space here. I need enough space here, like that. Then when you run this code, you'll get your scatter plot there. Okay. This is our scatter plot. This is the title. This is what goes to the main. This is bands. This is band. Bands like that. This is what we have. Then we have labeled the x-axis. This is what was initially blood dot glucose, then velocity dot shortening or shortening dot velocity. So we give them meaningful names. Then we want to add the bands now. I want to add the bands, the confidence bands. Okay. So we start by extracting. You see from this data frame here, my new data, I want to extract this particular column. So this data looks like this. This data frame looks like this. So what I want to do, I want to extract these observations. Okay, I want to extract them, then I can use them later on. So I want to assign this name, so I can call it new glucose. Those are my new values of X. So I want to assign this the name. This one should be from my new data in blood glucose. That's what I want to obtain. So just a quick look at it. This is how it looks like. So these are the observations. These are the observations, which are just the same as we saw earlier on. But now I want to use the matplot, the matplot function. There's matplot, there's matlines, and so on and so forth. So that's the function I want to use to get the multiple lines to superimpose the multiple lines on this scatter plot here. So I'll use matlines. Yeah, matlines. Then I say of what? New glucose on the vertical, on the horizontal axis. New glucose. That's my new set of observations. So my new glucose. Then I have the predicted. We can start with the confidence bands. Okay, so we can start with this one. And then I can put the line type. Which line type do we use here? We can say LTY, because there are 3 lines. There's a fitted line. As you saw from the output, we have 3 sets of observations. We have the fitted points, we have the lower confidence band, the upper confidence band. So I want each one of them to be in a different kind of line. Maybe the two limits to have the same, but the fitted line to look slightly different. So I want a set of line types here. So I wanted to pick line type number 1, and the others to pick line type number 2. So 2 of them will look alike. Those are the limits. And then what else can we put? We can also, so let's run it the way it is first. Then we see what we're going to get. By default, this is how it looks like. Okay, so these are the confidence bands, the upper scalar green and the lower confidence band. As you can see, they are curved at the center. They are very close to the line at the center here, because the estimation is most accurate around here. So the mean of fasting glucose should be around here, and the mean of shortening velocity should be around there. So that's why the bands are very narrow here around the center. I may want to change something here. I may want to customize the color, or I can start by line width. I can adjust the line width to make them maybe thicker or even narrower. So, and my choice for the line width is I can put all of them I can increase their width like this. So this is how wide they become. Okay. Then I can also I can also customize the color. So I can say color. I want the color for all of them to be, I want the color to be black for all of them. Okay. Color is black. I want all of them to be black. I don't want to use the different colors. Okay. So when you run that, they all become black like that. You have the option of using a different color, but I'm choosing that for now. Okay, so those are the narrower bands. Those are the confidence bands. So I want to, again, draw the prediction bands on the same axis. So I'll use the same code, but I'll change a few things inside there. So copy, then I have mat lines. So first I'll change this from the confidence to the predicted observations. Line type, I can use the same line type. There's no problem. I can use the same width, but I can change the color to green. I can use color green here for all of them. Okay. The problem is that you notice that this black line here will be overwritten by the green one. So it's good for you to note that we'll have a new set of upper bands, upper limits and lower limits, and the predicted values, the fitted values will be the same. So we'll be passing through the black line. So it will be overwritten. So like that, you can see. Okay, so we have the wider band, which is the green one, and the fitted lines. So the black and the green lines are passing in the same point. That's why the black one now has been overwritten. Okay, so basically that's how you draw the confidence bands. Then you can make your diagram much more informative by adding a legend. You may want to add a legend or to add a key so that somebody who reads your diagram can understand what is the green line, what does the green line represent, or the black one, and so on and so forth. So this is how you go ahead and add a legend to your diagram, or a key. A legend is what some people call a key. So legend, where do we want to place it? I want to place my legend somewhere here. I hope you can see my cursor. I want to have it here because I don't want the legend to overwrite my diagram or to be somewhere where it's not conspicuous. I want to put it here because there's some space. So you decide where you want to locate it. So my location will be around here, somewhere around 5. When X is 5, or I can say 4.5. I want it to be located around there. And when the vertical axis is around 20 there, so I can say not 20, 2.0, so 2.0. So that's the location where I want to see my legend. And then this is what I want to, this is how I want it labeled. So legend, this is how I want it to be labeled. So because we have 2 items, I'm going to concatenate the description. So we have in quotes here, confidence band with fitted line. So that's the first description. And then the second description, because there are 2 sets of lines that I'm describing. Okay. The second set of this one, the comma should be inside, sorry. So that's the first one. Then the second one here should be tolerance. I'll just call it tolerance band with fitted line. And that should be the end of that concatenation. Then which color? I want the color in the legend to match the color on the diagram. So color will be, the first one is using color black. Sorry, yeah, the first one was using color black, and the other one is using color green. So I say this is in color is, I concatenate again, then I say first one is black. And you put them in the order in which you want the lines to be labeled. Then the second one is green. Second one is labeled green. Then which line types? So line type, I've used the same line type for convenience. Line type is my line type is equal to C. Then I have 1 through 2. So I'm using the same line types I used in the earlier code. And then let me bring it here. Then I can also put the line width, the one that I used to insert the lines. So line width, I used 3 everywhere. Okay, that's what you have. So let's try to run that. We see maybe if it is going to give us something. If there's an error, we can correct it. So you see that's where you see how it happened. The legend is coming where I told it to go, but there's a problem. It is overflowing. You can see it is overflowing the diagram. So I want to compress this box and make it smaller so that it doesn't overwrite my diagram. And you do that by coming here and you add this function CEX. So this one will scale your, actually it is the explanation here. This is character expansion factor. Okay, so this one will adjust the size of the contents of this box, the legend containing your description. It will scale it down. So by default it is 1, but you can make it smaller. So I choose to put it 0.8. Okay, and I run the code again, then see what will happen. So if I run this again, so let me run this from the top here. So if you do that, you see, that's how it looks like. Doesn't look very nice. It's still overflowing. So I want to make it smaller. Maybe 0.5. Make this space even bigger. You got to make the plotting area bigger. Okay. Then okay. Then I want to, you see, so this is how the legend now comes in. So you find that it is not overwriting your diagram. So you adjust the size of whatever is in your legend using this function. Okay. There's some distortion because of what I'm doing here. So this function is important. This is how you scale it down so that it fits into a plot area. So basically that is it. That's how you can plot, you can illustrate your confidence and tolerance bands using R. Okay. So you see the first set of band is revolving around the straight line. Okay, but the green one is for any future observations. And that's why it's a bit wider, like this. And this is what we're saying will never converge to a single line. It will only become closer to plus and minus 2 standard deviations as you increase the number of observations. But the confidence bands, the black lines here, will become narrower as you increase the size of your sample. Will become narrower, showing that your prediction will be more accurate. So this just is the level of accuracy in your prediction, or this is a fluctuation that we can have of the line. So this is the random part. This is the variation of the possible variation or the randomness that is that this line is predicted with. This line is predicted with this magnitude of randomness. Yeah. So basically that is it. I hope you'll be able to replicate this on your own. I'll be giving you some work to do at home, but for today, I want us to stop there. Any question? So if there's no question, we're going to meet next week to look at correlation analysis.